Hello, I am Ahmad, and in this video, I am going to continue the last example that we had about the residual stress. In this one, we are going to solve it by one FEM software, here RFEM6, and to check the results, how it should be modeled in some kind of a FEM analysis software, and how we can compare the results, and also nonlinear material modeling in such software. Let's do it. The example was about a rod with the length of 1200 millimeter, fixed connected to both ends, A and B, and at point C in the distance of 400 millimeter from the left and 800 millimeter from its right. It was under a load with a magnitude of 220 kilonewton, and after that we remove the load. Phase 1 and phase 2. The material was assumed to be elastic, perfectly plastic, with sigma yield of 180 megapascal and the corresponding yielding strain 0.0018, or elasticity modulus was 100 gigapascal. So in the software, for example, in here in RFEM, we need to active the nonlinear modeling. So here, when you come to the add-on modules, you need to check nonlinear material behavior to have such a material, and then we can have the material. So here I'm going to have a new material, and I want to name it elastic, perfectly plastic, basic, and it's going to be nonlinear elastic for the members. You can find out, for example, from European metal, and we do not have such a material. You select something, for example, here, Cooper, but we need to change the name after that. Elastic, perfectly plastic. It's a material, metal, and nonlinear. Then we check user-defined material. We change the elasticity modulus to 100 gigapascal. The rest are fine for now. And here in the next tab, we have the parameters relevant to this material, of which here is going to bilinear, and we assume that the strain hardening is 0. Fy in compression and tension, we assume that it is 180 megapascal, and material values, these are the value that we just entered as elastic modulus of elasticity and also yielding stress. Then we can have one element, one member. In the section, it was D30. For the section, but by default, I have HE220A, and here I'm going to introduce one new material, which is a round bar. The material is elastic, perfectly plastic, and then we need to have the diameter of the bar, which was 30 millimeter, and the rest looks to be fine. So it was 1.2 meters. This is 1 meter at the moment. I increase the length by moving the end of the element in X direction for 200 millimeter. So here we can see that the length of the element is now 1.2 meters. Now, if you want to cut one element in RFM, you can go to member and then divide member. For division also you have some options. Here we are going to have the distance, and from the beginning of the element it's going to be 400 millimeter. Now we have point A, C and B. I select point A and point B and assign a rigid support. Now your model is ready. We need to apply the load. We open the active load case edit box. So usually I copy or I make a new load case instead of modifying the current load case. Usually the first one is self-weight and always the active self-weight is in the zeta direction. I create a new load case and I write loading. The other options are fine for now, and as we can see, self-weight is not active here. Then we have a nodal load that we can apply to point C, and if you remember, it was 220 kilonewton in X direction, and in this case it will be in negative side. $220 kilonewton in the negative direction of X applied to the point which is located 400 millimeter from support A. And then show result. Here 1.05, and we can see the X direction deformation. Also, if we go to the member force, we can see that the AC element is under compression 127 and the other side, which is BC, under tension of 93. And we got the same result, if you recall it. Now we want to unload this bar from 220 kilonewton. There are one option that we can use, but we have to be careful when we are unloading the system. Here we have consider initial state from, and we have self-weight. Now we are going to use the results from loading, and here we can select the strain. You can select also other options to check to understand it better how it works. And now in this case I apply the load in the opposite direction in the same position with the same value 220 in X direction. And we can also solve this load case. Here if we check the deformation, it's 0.139 millimeter in the opposite direction of the earlier load, and it is better if we check from the S strain as well. So here we can see that the S strain is 0.35 and in the other element it is 0.17. If we come back to the loading analyzers, it was 2.63 and 1.32. 1.32 is relevant to the same value that we calculated. So if we calculate 1.32 10 power by minus 3 times 800 millimeter, it will be exactly 1.05. We calculated earlier. And if we divide this value by the length of 400 millimeter, it will be 2.64 power by 10 power by minus 3, which is given here. We calculated the same results in the earlier example and video. If we check it from here, also we have 1.052 in the loading. And if we go to the unloading case, we can see that the S strain is not the same as the previous one. It is 0.35 and minus 0.17. So in this case, we can see that the force in the element, if we hit the normal force, we can see that the load in this element is 127. And if you remember, we checked and it was not 127, it was 146. The reason is that when it is solving the structure, it assumes that the original load is 0, not minus 127. As a result, it starts to calculate from 0 phase, which means that you have only 127 kilonewton capacity for this element. But we know that it should be 254. At least with RFM, I could not find a way to calculate exactly loading and unloading with the reasonable results. For example, if we use ANSYS or other advanced software for that, for sure we can have the time steps and we can load and unload the structure and check in every step what the situation is. But here there is a trick if you want to use that and have the same value that I will show you. So if you are using this method for applying the initial case for other load cases to be applied to a new load case, be careful about this plasticity. At least I could not find a way in RFM. For the better solution, it is good if we come back to the original loading. I will copy this in 5 meters in Y direction to have both structures at once. So assume that this is loading and this is unloading, so it should be in the opposite direction. And now in the unloading, these two elements are with higher capacity for elasticity. One good way is have another material and apply that material to these two elements. For that, I will open the material box and I will just copy this elastic, perfectly plastic material. And I will use it as reverse loading up to 360. In each direction, we have 360 megapascal capacity. And also we need to have this section also with a new material. So we need to open sections box and we can make a copy from this round 30H. And instead of elastic, perfectly plastic, we can use reverse loading. Now, if we look at this part, we can see that it's with the material number 2, and this is with material number 2. So for reverse loading, you need to change the section to the round 30H. but this time with the reverse loading material. Now we can solve this for the material and for the load configuration. Now here we can see that in the loading, so the element AC is taking the load up to 127 in compression, and in reverse loading it will take to 146.67, the same value that we received in our calculation. And also BC in the loading, it will take the load up to 93 kilonewton, and in the reverse loading 73.33. Also we can check the strain from here. What kind of strain do we have? Or in a better way to calculate with the deformation. So in the loading phase, it goes up to minus 1.052, and then it will come back for 0.83, which means that minus 1.052 plus 0.831, and it will be 0.22 in the negative side. It means that point C will shift towards A or to the left with 0.22 millimeter as a permanent deformation. That's how we can summarize this calculation. And if you want to see a better interface for the deformation, if you come to the member and check the UX, you will see this type of hatched area to show the deformation at each point. Here we can see that point C in the loading will go through to the left with minus 1.05 millimeter, and then in the reverse loading it will come back to 0.83, and with the sum of these two deformation values we can have the permanent deformation at point C. That's it. We modeled the same rod for permanent deformation with nonlinear material modeling in RFM, and we could see how the results can be matched with what we calculated by hand. So it's very important to understand how the software works. The concept is the same in any software. The only thing is modeling a simple element, simple beam, simple column, whatever is the task, and understand what the software does. And after that, we can ensure that, okay, our model is working as we expect. That's all, and thank you for watching. See you next time in next video. Bye.